Imagine a theory that could unify everything we know about the universe, from the tiniest particles to the vastness of galaxies. A theory that rewrites the rules of physics. This is string theory, a bold, controversial, and mind bending idea that's been captivating scientists for decades. But what is it? How did it come to be? And could it really be the key to understanding reality? Let's dive in. To understand string theory, we need to start with a problem. By the mid 20th century, physicists had two pillars: Einstein's general theory of relativity, which describes gravity and the large scale universe, and quantum mechanics, which governs particles and the subatomic world. They are both incredibly successful. General theory predicts black holes and the expanding universe, while quantum mechanics powers modern technology like computer and lasers. But there is a catch. These theories don't play well together. When you try to combine them, like in extreme places such as black holes or Big Bang, the math breaks down. We needed a new framework, a theory of everything. Enter the 1960s, the physicists were searching for way to unify these realms. This quest set the stage for string theory. String theory wasn't one to solve this grand problem. It turned into it. In 1968, physicist Gabriel Veneziano and others were studying the strong nuclear force, which holds particles like protons together. They found a mathematical formula that described particles' interaction beautifully, but it didn't quite fit existing model. By 1970s, Yusiro Nambu, Holger Nelson, and Leonard Susskind realized this formula could be explained if particles were not points but tiny one-dimensional strings vibrating at different frequencies. Each vibration mode corresponds to a different particle, like notes in a guitar string. This was a wild idea. Instead of a zoo of point-like particles, the universe could be made of these vibrating strings, just 10 to the power minus 35-meter long, far smaller than we can probe. But there was a problem. The math only worked in extra dimensions beyond the four we experience: three space and one time. Extra dimensions? That sounds like science fiction. String theory suggested the universe has 10 or 11 dimensions, but most are compactified, curled up so small that we can't see them, like a straw that looks 1D from far away but is 2D up close. These extra dimensions, described by a complex shape called Calabi-Yau manifolds, determine how strings vibrate and thus what particles exist. In the 1970s, the idea was a tough sell. String theory also predicted a particle that moved faster than light, a tachyon, which seemed unphysical. By the mid 1970s, string theory was nearly abandoned. Quantum chromodynamics, a rival theory, better explained the strong force, and string theory's quirks made it seems like a dead end. But a few physicists saw potential. One big discovery came in 1974 when John Swartz and Joel Schreck realized string theory include a particle with the properties of gravitation, the hypothetical carrier of gravity. Could string theory unified quantum mechanics and gravity? In 1980s, string theory roared back. John Swartz and Michael Green showed in 1984 that certain versions of string theory were mathematically consistent, avoiding anomalies that plugged earlier models. This sparked the first superstring revolution. Suddenly, string theory wasn't just about particles, it was a candidate for the theory of everything. By this time, physicists identified five consistent string theories, each required 10 dimensions and incorporating supersymmetry, a principle that predicts partner particles for every known particle, balancing the universe forces. These five theories were exciting but confusing. Why five? Were they all correct? Or was one of them true? The field was buzzing, but string theory faced skepticism. It made predictions we couldn't test with current technology, and some called it unprovable philosophy. In 1995, Edward Witten ignited the second string revolution at the conference in California. He proposed that the five string theories were different facets of a single deeper framework he called M theory, which required element dimensions. The M is mysterious. Some say it stands for membrane, mother, or just mystery. M theory introduced not just strings but higher dimensional objects called branes. Think membranes or surfaces that strings could stick to. These branes opened new way to understand black holes, gravity, and even the Big Bang. M theory also connected string theory to cosmology. For example, it suggested our universe might be a 3D brane floating in a higher dimensional space with gravity leaking between dimensions. This could explain why gravity is so weak compared to the other forces. String theory hasn't been experimentally confirmed, but it's far from just theory. It's led to breakthroughs in mathematics, like new tools for geometry and number theories. It's deepened our understanding of black holes. String theorist Andrew Strominger and others showed how black holes store information, resolving a paradox in quantum mechanics. String theory also inspires cosmology, suggesting models for the multiverse, where different universes have different physical laws based on how extra dimensions are shaped. String theory's math is so powerful that it's even used in condensed matter physics to study materials like superconductors. It's a testament to how a theory about the universe's smallest scale can impact many fields. Despite its promises, string theory has critics. Its predictions, like extra dimensions or supersymmetric particles, require energies far beyond our current experiments, like those at Large Hadron Collider. Some argue it's untestable, as it allows a vast landscape of possible universe, maybe 10 to the power 500 configurations of extra dimensions. You can imagine 10 to the power 500? No, you can't. This means 500 zeros after 10. Even 12 zeros means a trillion. So you can think about it, how huge this number is. This makes it hard to pinpoint our universe's version. Critics like physicist Lee Smolin says it's too speculative, diverting attention from other ideas. String theorists counter that it's still young, and its mathematical elegance suggests it's on the right track. So, where does string theory go from here? New experiments like next generation particle accelerators or gravitational wave detectors might find hints of extra dimensions or super mystery. Advances in quantum computing could simulate string theory's predictions. Cosmological observations like those of the cosmic microwave background might reveal signatures of multiverse. String theory remains a leading candidate for a theory of everything, but it's also competing with ideas like loop quantum gravity. Only time and more data will tell. String theory is a journey into the unknown, a bold attempt to decode the universe's deepest secrets. Whether it's the ultimate truth or a stepping stone, it pushed the boundaries of human imagination. The universe is a symphony, and string theory might just be its score. What do you think? Could string theory be the key to everything? Let me know in the comment section. And if you like this video, please share this video with your friends and hit the like button. And for such more amazing content, subscribe my channel. Thanks for watching this video. See you guys in next video. Bye bye. Being something.